Okay. So the functions here are y equals root x and y equals half x. I like to label my functions just so I know, right? Get a visual representation. The region in between them is this. And so first what I want to do, right, is to really get that region is I want to figure out what points of intersection I'm talking about here. So if I set the two functions equal to each other, square both sides, I get 1/4 x squared. So 4x is x squared minus 4x is 0. And when I factor, x is 0, x is 4. So this first point here is 0, 0. And here, x is 4. And for the y value, because at that point the two functions are equal, I can plug x into any of these functions and get 2. So those are the 2 points of intersection. Okay? All right. Next. The question is asking me to find the volume of the solid generated by revolving this region around the x-axis this way. When I revolve that region around the x-axis, this solid part kind of looks like this. 1, 2, 3, 4, -2 here. It looks like this and this, right? When I revolve it, that's what it looks like, right, in 3D. So this is like a slicing of it. And this is the region where I'm looking. It's solid here and then hollow inside. So basically I want the region of the shaded, the volume of the shaded region, right? Okay, so my cross section is this. I've got one large disc here, another small disc here, okay? So if I go one by one here, I need to find the radius of the large disc, and it's always going to go from the axis around which you're rotating, this is the x-axis, up to the outermost perimeter, right? That length here, that's capital R, and it's equal to root x because that's the function there. For the smaller circle, this is the radius. Again, it goes from the axis of revolution up to the closer graph. So little r is half x. So my volume then is pi big R squared minus little r squared dx, right? And because everything is x, 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 I take my x values of the intersection and I go from 0 to 4. Okay? Integrating, this gives me 8 pi over 3. Okay, so again, I've been getting lots of questions. Do we use the calculator? Do we not use the calculator? For the homework, I said to use the calculator, but that's under the assumption that you already know how to integrate these by hand, right? And right now, I want you guys to build the calculator skills. However, make sure you still remember how to integrate by hand. Don't let that skill get rusty. Later on, we're going to do both equally. Okay, now we're going to change things up a bit. Now, this next question says, to find the volume of the solid generated by the same functions, but now by revolving the region about the y-axis this time. All right, so now I'm going to take that same region, but revolve it around the y-axis. And when I do that, I get something different, right? That's a completely different solid. Do you see how different the two solids look, right? So by revolving it around another axis, now I've got another solid. Another solid means a different volume, okay? Now, my discs look like this. This is the outer disc, and this is the inner disc. Well, now when I'm going horizontally, I need to switch and I need to solve everything for x in terms of y. Okay, so solve equations for x in terms of y, right? So my equations were what? It was y equals root x, which means x is equal to y squared, right? So here x is equal to y squared. And then I had y equals half x, so x is equal to 2y. X is equal to 2y. Okay, now I need to figure out the big radius and the little radius. The radii go from the axis of rotation out. The big radius goes out to the farthest function. In this case, it's 2y. Okay. The little radius goes from the axis of rotation out to the closest function. In this case, it's y squared. All right. I am choosing my words very, very carefully here, right? Because these are the words that we're going to use for the next, varieties that we're going to do. So radii goes from the axis of rotation out to the farthest function, axis of rotation out to the closest function. All right, you're going to carry that language with you. So now, what's the volume? Volume is pi, okay? Big radius is 2y quantity squared minus y squared quantity squared. This time though, it's dy, right? Because we're going, around the y-axis, so everything is horizontal. And then, since it's y, my limits are also the y-coordinates, so it goes from 0 to 4. Okay? And when you integrate, the volume this time is 64. Huh?
Oh, but I thought the
Oh, 2.
4,2, I thought.
Oh, sorry. Yes, I messed that up. 4,2. Sorry. Thank you. So then it goes to the y value, which is 2. Thank you. All right. So this time the volume is 64 pi over 15. So do you see how that proves it's a completely different shape? All right. Okay. Next. You guys ready to take it up another notch? I mean, it's happening either way. All right, so because, right, x-axis, y-axis are kind of overrated, right? It's like, hey, why just revolve around the axes when I can revolve around some random line, right? So why don't we do that? So next, we're going to talk about what happens if you rotate about a line other than the x-axis or the y-axis. Okay. All right, so let's talk about first how it is that we are coming up with these radii, right? Remember this, each radius is always the upper minus the lower, right? Upper minus lower, right? That's how we always get that length. Okay, so there are 4 situations that we're going to consider. First situation is, what if the line of rotation is below the region to be rotated? Okay, what do I mean by that? Well, let's take a look at this example. We want to rotate the region bounded by y equals root x plus 2, that's this one, and y equals e to the x, about the line y equals -2, that's here. All right, so now I'm taking that region and revolving it around this, that y equals -2. So what happens when I do that? When I do that, I get something that's symmetric. And I'm not really that good at drawing these, but I basically get something that looks like this here. Okay? So basically what happens, this is the shaded region. It's the mirror image of the one above. And here, there is an equal amount of empty space, right? Because I'm taking this whole thing and now revolving it around that. all right? So now what do my radii look like? What do my discs look like? This is one disc, that's the larger disc, okay? And I want to figure out what that big radius is. Okay, what did I say before? The big radius is the distance between the axis around which it's being rotated, the line around which it's being rotated, out to the farthest function, right? Is that what I said before? It's from the rotation out to the farthest. So how do I calculate that? Well, it's the upper minus the lower. The upper is y equals root x plus 2 minus, what's the lower? Y equals negative 2. Okay? And then what's the little radius? That's this disk. What's that radius? Well, it goes from the rotation axis up to the closer curve. So the little radius is the upper e to the x minus the lower negative 2. Watch those double negatives there. So what happened then? What did we end up doing? For the big radius, we ended up doing the outside curve minus the line, negative 2. And for the little r, we did the inside curve minus the line, negative 2. Okay? So capital R then is root x plus 2 plus 2, and little r is e to the x plus 2. Okay, what about points of intersection? I'm not going to, you're going to use your calculator to do this. I'm not going to do it right now for the sake of time. But when you find the points of intersection, suppose this is AC and BD. Let's see what the volume will look like. Pi, big R, x plus 2 squared minus little r squared dx, because my expressions have dx, x's in them. And the bounds go from A to B, the x coordinates. All right. How are y'all doing so far? Any questions? All right, so what if we went to the next situation where the line of rotation is now above the region to be rotated, okay? We're gonna rotate the same region about the line y equals 2 here, okay? And again, this is y equals root x plus 2, and then this is y equals e to the x. All right. So again, I've got big radius and little radius. This time, I'm not going to draw the discs. I'm just going to draw the radii, right? Okay, what did we talk about? What did we say about the radius? It goes from the axis around which it's being rotated, that's this line, out to the farthest curve. Where is the farthest curve? This one. Okay? And then it's always the same. I always do upper minus lower. So big R is the upper y equals 2 minus the lower e to the x. If you stay consistent with your language, the math just falls into place, right? Just stay consistent with the language. And then the little radius, from the radius to the inner curve, to the closer curve, that's 2 minus root x plus 2. Cool? Okay. My limits of points of intersection are A comma C, B comma D. So what does volume look like? Pi, big R squared minus little r squared dx. Okay. And then the limits of integration go from a to b. If I were grading this, okay, I would give 1 point for the pi, 1 point for the integrand, 1 for the limits, and 1 for including the dx. Each of those play an equally integral, integral part in this volume, okay? All right. All right. Should we do one more? Let's do one more. Okay, so we did up, down. Okay, what if the line of rotation is to the left of the region to be rotated? All right, we've got some fresh curves now. Well, not really, but we've got x equals y squared minus 2, right? That's this one in blue. X equals y squared minus 2. And then I've got x equals ln of y. And I want to rotate this around the line x equals -3. That's here. Now, because I'm rotating around a vertical line, that mimics the y-axis, right? I'm rotating around y. That mimics the y-axis. So everything is horizontal. So instead of upper minus lower, I'm going to do right minus left. Okay? All right. So what does that mean? If each radius is going to be right minus left, let's draw our radii. The big radius goes from the line of rotation out to the outside curve, the farthest curve. So big R is right minus left, ln of y minus -3. So that's ln of y plus 3. Little r goes from the axis of rotation out to the closer curve, and that's y squared minus 2 minus -3, y squared plus 1. That's probably the hardest part, where you have to visualize. And then the rest, right, you just build using pi r squared minus r squared. So pi r squared, ln of y plus 3 squared minus y squared plus 1 squared dy. And now what about the bounds? If this point is AC and BD, right? And if these are all y's, then this is going to go from C to D, right? So what happens here is, I've got like discs like this, right? And I'm just like integrating and finding all of the volumes of all of the discs. Okay. Last one. You guessed it. The axis of rotation is to the right. This time we're revolving the same functions around the line x equals 2. Okay. So here I've got x equals y squared minus 2, x equals ln of y. Okay. Big radius goes from axis of rotation out to the farthest curve. And then I do right minus left. So big radius is 2 minus y squared minus 2. And then simplify that and we get 4 minus y squared. 4 minus y squared. Little r, axis to closer curve. 2 minus ln of y. So this is A, C, B, D. And we're gonna, okay, so it's gonna be 4 minus y squared, squared, minus 2 minus ln of y squared. Okay, is that right?
Is it C to D?
It is C to D. What else did I not do?
The pi.
The pi. Okay, those two were intentional. Okay? Okay? All right. So this is how we do volume, right? I think I'll stop the recording here.